did I miss you? Oh my goodness, and there's Aaron, Sean, Ollie, Ashley. Welcome, welcome, welcome. Okay, guys, whoa, now we need to calm down. We need to calm down, okay? I need you guys just to update me. As far as I am aware, you guys very briefly ran through magnetism and you ran through, oh, you did charge quantization. Sandy, I see the question. I promise I will deal with it. You guys didn't do magnetism. You did charge quantization. Okay, I can pick up from there. Guys, just give me a second because obviously I didn't prep this lesson. But lucky for you, this is one of my strong points. So, those of you with a study and master, I want you to go to page 100 at, pardon me, 54. Who's got a, no, I lied, Oxford, 154. Who's got a study and master? Study and master, you need to go find my electrostatics page, please. Dilo, I need study and master pages, please. Okay, we're just gonna wait for Mr. Dilo, who's a JGM kid. Okay, we've got Kamal saying, okay, thank you guys for confirming. 190 in the study and master. Okay, I might be repeating a few things. Oh, Miss P, you're on the ball. So those with you with Doxky Enzas, 123. Okay, guys, so now we all know where we need to sort of be in our textbooks. Fantastic. All right. My speaker sounds weird. It might just be me. I had an afternoon nap and then a very important phone call woke me up and said, my kids need me. Sandy, in the Oxford, it's 154. Hey, Miss P. All right, guys. So, I might be repeating what you have already heard, okay? My speaker is weird. Let's double check. What speaker am I using? Let's try this one. Okay, is that better?
Please just check your sound for us.
Have you got me again?
We got you again.
Okay, cool. Sorry, guys. I'm just playing. Okay. No, you know me. My tech skills are not bad. They're just not brilliant. Okay. Cool. So, I'm glad that's better. So maybe I just needed to push a button. Okay, guys. So, you all got my whiteboard. Okay. I might repeat a few things that you've already heard. Okay. But let's all make sure that we are solid on the idea of charges. Okay, now before I start, you guys know my big love is chemistry, right? But don't panic, this is physics, okay? I promise this is physics. However, we need to remember a little bit from chemistry. Okay, when we did metallic bonding, remember that we said that the electrons become delocalized, so they are like free to move. They don't belong to any one atom. They can move from one atom to the next freely. And that exact point is why we have electricity. Okay, electricity is quite literally the flow of electrons. Okay, and that is the start and finish of the amount of chemistry that you need to know for this. Okay, now, if we think about an atom and its electrons, then we have this really strange word, which you guys just whacked down there in front of me, called quantization. Okay, now it is a super weird word, okay, and the problem with the word is that the definition is even weirder. Okay, quantization tells us, I know it's weird to spell too. Quantization tells us that in the world, in the whole universe, there are certain pockets, okay, that we cannot break further. All right. And the pockets, the smallest pocket, they've decided to call a quantum. Okay. So, this is only really needed, these two definitions, when you get to grade 12. Okay? These two definitions are very specifically in grade 12. It's in paper 1. It's the last question. You don't have to worry about that. Okay? Now, you would have remembered when we were doing waves that we also spoke about quantization and quantums. Erin, you're not in a wrong space, okay? A quantum can be any smallest unit, okay? So when we did energy with waves, we also had these concepts, okay? We said that each wave carries a specific amount of energy, okay? And that amount of energy we determined was a photon, okay? Now, when we take this idea of quantization and a quantum and we apply it to electrical circuits, okay? Electricity. Sandy, I like that. Sandy says her teacher says it's like a packet of rolls in the shop. You can only buy a packet of 6. You can't buy a packet of 5. Exactly. So your packet of 6 is your quantum. Okay. That's a very good way of putting it, Sandy. I like that. Okay. Tyrese, I agree. Very smart. Okay. So now we're going to take this packet and we're going to apply it to electricity. Okay. Now, when we work with electricity, we deal with electrons. Sorry about the yapping puppy in the background. Okay. Now, electrons is a part of an atom. Okay? And what they determined through experiments, and I say they, because I definitely ain't smart enough to have figured out these experiments, is that each electron has a charge of 1,6 times 10 to the power 19 coulomb. Okay? C is for coulomb, after the dude who did the experiments. Guys, I'm just going to rewrite that. That looks terrible. Dunk. Dunk. That's better. Okay. So each electron has a charge of a really tiny little amount. Okay? Right. And that means that when there is transfer of electrons, transfer of charge, okay, then it has to be some or other multiple, whole number, of 1,6 times 10 to the power 19. And that is what we look at in electrostatics. Okay? If you think about the word electro, we're talking about electrons. Static, not moving in a flow. Okay? So electrostatics is when we investigate, when we look at, when we study objects that have static electrons, okay, and a lack of or too many electrons, which then gives us charges. Okay, now guys, this idea of electrostatics, you don't do again in grade 11 or 12. But this idea of transfer of electrons, I have very sneakily seen squeezed into grade 12 papers. Okay, because there is Coulomb's law, okay, in grade 11, which is tested in grade 12. Now, Poppy asked a very good question. Ma'am, isn't it negative because it's electrons? Okay, Poppy, I'm so glad you asked that question. That is such an amazing question. Now, let me explain to you what they mean by this value. Okay, they determined that an electron has a charge of 1,6 times 10 to the power minus 19 coulomb. So, if an object, I don't know, object X, lost one electron, okay? So object X gave an electron to something else. That means that object X will have a charge of plus 1,6 times 10 to the power 19 coulomb. Okay. So if object Y gained an electron from somewhere, then object Y will have a charge of minus 1,6 times 10 to the power minus 19 coulomb. Or, good job, Erin, a multiple of that number, depending on how many electrons it gains or how many electrons it loses. Okay, so this is the idea of quantum or quantization of charge. Okay, not quite that bad. Right, now, any of you ever did this fun thing where you wear socks and you drag your feet over a carpet? Fluffy carpets are the best. And then you turn all the lights off in the house and you see the sparks flying. Or if you've got, like I do, my mom loves knitting me jerseys, okay, and they're always from like proper wool. And so whenever I put the jersey on or take the jersey off, okay, and you put all the lights off, then you can see the sparks flying. Okay, if you haven't seen it, you definitely need to go and try. Now, the one thing I'm pretty sure you guys have all seen is lightning. Okay, that lightning, the spark flying, okay, that is electricity jumping either from the ground to the clouds or from the clouds to the ground. Okay, now depending on which way it goes will be, say for example, the cloud somehow picked up a really positive charge, okay, then the electricity from the ground will jump up in that arc all the way to the cloud. And the electricity jump is that spark you see. Okay, now that means, yes, Tyrese, I agree. It was really beautiful. Erin, I love it. My mom's knits. It's like the favorite thing. Sibusishu, yes. Okay, and I know that sounds really weird because in our brains we always have that lightning jumps from the cloud to the ground. But it depends on which part of the two has more positive and more negative bits. Okay, so it can jump from the ground to the cloud. Okay, how does it get to the cloud? Now that's the weird thing, Arthur. As much as we know about electricity, okay, and if you take the song, thunderbolts and lightning are very, very frightening. Okay, so yes, there would be a roof in your house, okay, Arthur, but if there's a big cloud above the ground and there's nothing in between the cloud and the ground, then because the cloud is very, very, very negative, Ashley, yes, good job. Because the cloud is very, very positive, okay, then it will pull the electrons from the ground. I know, it's scary. And the worst, well, not the worst thing, the cool thing is that scientists still don't really understand lightning, okay? Like there's lots of bits that we understand about it, but we don't understand all of it. Okay, so what I want to show you guys is what happens on a small scale between two objects, okay, that are differently charged. Man, can you see it when electricity jumps from the ground to the clouds? You can't always see which direction. You need like a really slow-mo camera to be able to see from which direction to which direction, okay? But if you can find a video on YouTube, it's like flippin' awesome. Yes, Erin, I agree. Erin, if you've got a link, then please post it here so that people can go and watch it. It's like really, really cool. Okay, so we're now going to take that idea of lightning, okay, of electricity jumping from one object to another, okay, and we are going to look at that at a smaller scale. Yes, Sandy, the flash is like super fast. So you have to have a camera that records at like 1,000,000 frames a second. Okay, and I know my husband just laughed at me because I don't think that's possible, but anyway. Thanks, Erin. Okay, so let's say we have two metal spheres. And they are, ooh, that's a very squiff stand, but anyway, on isolating stands. Okay? And let's say, looking for an example. Oh, this sphere has a charge of +3, don't be scared, microcoulombs. Don't be scared. I've got you. I know that's a weird sign. And this one has a charge of -1 microcoulomb. Let's deal with the weird sign first, shall we? Micro is a little bit like milli and nano and pico and mega and giga and kilo. It means that I take the number and I multiply it by 10 to the power -6. Yes, it is two people talking, quite literally. Okay. So this sign here simply means, okay, that I multiply it by something. It's like when I have millimeters, for example, then it's 10 to the power -3, okay? So milli is the prefix, meters is the unit. Ooh, not that way around. Unit, okay, cool. So that's what that funny Hong Kong sign means. Okay. The other one that you might see in electricity is nano. Okay. And some of you might have heard of nanotechnology. And luckily, nano is easy to remember because it's -9. Okay. Those are the two that you tend to see with electricity. Tyrese, I'm sorry your brain is fried. Mine's trying to wake up from a nap, so I feel you, dude. I feel you. Okay, so let's look at this. Okay, so if this one, let's make it A, and let's make it B. If A has a charge of plus 3 microcoulombs, okay, then that means, because it's plus, that it has lost electrons, okay? And because this one is minus 1, it means that it has gained electrons. Okay, so now, question. If I touch A and B together, and I then put them back, which way do you guys think the electrons are going to jump? Think about lightning. Okay. From B, Arthur, you're saying from B to A. Guys, they have to go from one to the other. Okay, we've got a couple that are saying from A to B. Okay. All right. So think about this carefully, guys. This one has too many electrons. This one does not have enough electrons. Okay, remember, I can't move protons, guys. They're like part of the nucleus. They are stuck. They cannot go anywhere. Jared, you are right. Okay, so listen why. Whoa, listen why. Because B has too many electrons and A does not have enough electrons, when I touch the two together, the too many electrons will go from B to A. And it will do that until the charge on A is equal to the charge on B. Okay? Right? We can't create electrons. As much as we would like both of them to have no charge, which would be fantastic, we can't create electrons. We can only transfer electrons from one object to another. Positive 3 is more than negative. Yes, Ashley, I know. So, someone give me an idea. Do you think both of these are going to be negative, or both are going to be positive, or are they going to have zero charge on them? Take a stab at it. If you're wrong, you're wrong. Who cares? Take a guess. Both positive. Jared did the maths. I have a couple saying negative, 0. Okay, so I know that you guys want the charge to be 0. Okay, that is what I would like to. But we do not have enough electrons in this system to make both of these equal to 0. Okay, we cannot bring electrons in from the outside. We can only have electrons from B to A. Okay, so the electrons in the system is stuck. They can't escape, and we can't have new electrons coming in. Okay, this is like North Korea. Kodli Marie, welcome. We are busy talking about quantization of charge and lightning and electrons going from one place to another. Yeah, Ali, I know North Korea is really sad, okay? But it helps when we think about closed systems. So, Adrian, that is exactly what we are going to do, okay? But we do have a little formula. So, we have that Q, so this would be the final charge on both. So the charge here and the charge there, okay, is equal to the charge on A plus the charge on B divided by 2. Okay. Mooi. Good, Adrian. Jared, guys, you clearly know the formula. So it's going to be plus 3 microcoulomb plus -1 microcoulomb divide by 2, okay? So plus 3 minus 1 is plus 2. Plus 2 divided by 2 gives me plus 1 microcoulomb. Okay, so that means that after I've, let me just zoom out. No, that's zooming in, wrong way. Right, so after I've touched A and B, the electrons jump from B to A until they both have the same amount of charge. Now the question that follows this one is always, how many electrons were transferred? Okay, this is where, this thing, this quantization of charge of an electron comes in. Now, the question is not how much charge. Yes, Adrian, close, basically that. The question is not how much charge, the question is how many electrons were transferred, okay? And that gives us this horrible equation. Okay, I don't like this way of writing it. Ma'am, if I don't put the plus in front, will I get it wrong? No, it is still right. Okay, I just write the +1 because you guys know me. If I don't write pluses, then I don't write negatives. Dum, dum, dum. Why do they write it like, no. Okay, so this one here. Miss P, you should know me by now. If I don't do something the same every single time, then I never do it the same. Okay, so, right. The number of electrons times the charge of an electron tells me the total charge. Okay, but listen to the question. How many electrons were transferred? So yes, Jared, we are getting to delta Q. Delta Q refers to the change, delta, change in charge. Guys, I'm going to sneeze in just a moment. I apologize. And yes, Jared, final minus initial. Oh, give me a second. Oh, sorry. Thank you, Aaron. Okay, right. So, change in charge. Now, my students always ask me, ma'am, which one? The same number of electrons that go from B will go to A. Let me say that again. The same number of electrons that B loses, A will gain. Okay. So, when you calculate change in charge, it does not matter whether you go, how much did A gain, or whether you look at how much B lost, because those numbers are the same. Okay? The number you get here for change is simply referred to which way the electrons went. Okay, Tyrese, delta Q means the change in charge. Okay? Today we're going to calculate how many electrons, like literally teeny tiny little electrons, went from B to A. Okay? Now again, the kids often ask me in a class, ma'am, do I calculate the change on A or the change on B? And the answer is, it does not matter, because all the electrons that leave B is gained by A. Okay, so this is Ben. I'm liking blue today, I don't know why. To what time is this class? We started late, so I'm going to push it as long as the moderator is going to allow me to. Okay, so +1, guys, is the final charge. Nah? I'm going to use A. I don't know why, I just decided. So, I'm working with A. So, +3 is going to be my initial charge. Okay, I will see if I can squeeze in doing number B as well. Miss P, I'm not promising anything, but I do have a plan in the pipeline, so don't get too excited. Okay, so we are working with number A. Now, so the change in charge is final minus initial. So it is +1. Yes, you don't have to write the +1. Oop. You see, that's why guys can't make me talk and write at the same time. Minus, because that's in the formula, +3. And remember, we're working with microcoulombs. So +1 minus 3 is -2 microcoulomb. Okay, so this is the change in charge, and now we have to go and calculate how many electrons is it. Is it always going to be smallest number? No, it depends on which of the spheres you choose. If you guys let me get through this one, then I will try to do from B to A. Okay, so I'm going to stick with blue. Now we're going to use this formula. Q equals, let's go delta Q, equals N QE. Go. So -2, and now we have to keep this thing in mind, times 10 to the power -6. Okay, equals N, meh. That's what we're calculating, times charge of an electron. Tom, tom, tom. Erin, of course this is easy. All science is easy. Just need to make it fun. Okay, guys, can you see the maths here? I go -2 there, divide by that thing. Sorry guys, hunting for a calculator. Someone got a calculator? Quickly do it. I found a calculator. Yes, my voice changed. I had to get up and run to it. 2 exponent -6 divided by 1,6 exponent -19. Right. Dum dum dum. 1,2. Ooh, that's minus. Times 10 to the power 13. Guys, that's a hell of a lot. Like, woo, lots. Okay. Now, it's negative. Why is it negative? Let's look. Why is it negative? We said that electrons went from B to A. Okay? So you have lots of options here, like crazy amounts of options. And now, Poppy, I think, asked it earlier about the negative. You can now say, but hang on, the charge of an electron is minus. Okay, and then this becomes plus. This means that A gained 1,25 times 10 to the power 13. Guys, that's a lot of zeros, nah? Electrons. Right. It gives you a 0. What gives you a 0? Oops. Okay. I have homework for you. Dum, dum, dum. Your homework, explain why I put the 9s in. Okay, that's the last thing I'll do. Diaries. Okay. Now, Avela, sorry for jumping up and down. The charge of one electron is 1,6 times 10 to the power minus 19. Okay? Whoa, whoa, whoa. Slow down. It's okay. 1,6 times 10 to the power 19. Okay? Jared, I want you to press pause on doing that. Just whoa it. Okay? And then, Jared, I want Jared, next week, Monday, when we start, I want you to start us off with your explanation of doing it scientific notation. Okay? And what I'll try and do is take like a little video of mine, okay, to push it on. Yes, Jared, I'm sure. Okay, so someone asked, why am I changing it to a negative? Okay, when I know the charge of an electron, by the way, this value is given, you don't have to remember. They just give me this value. But we know that electrons are negative. Okay. And so when I am looking at transfer of electrons, I make the charge of an electron negative. Okay. Guys, your homework. Yep. No, other way. Right. All of you. I'm trying to get everything in. There we go. I want you to go do the calculation I did for A, for B. Right? So, for B, I want you to go and calculate. Just stay with me. I want you to calculate, firstly, the change in charge and then the number of transfers. Okay? Guys, you got it? Right. Then, Jared, you are starting us next time with an explanation on your calculator. Do not drop me. Okay? Monday 3, I want to see you. Deal? Deal. Okay, guys, that is all we have time for. Jared's going to start us off. I am going to start us off with this explanation. Okay? And then we will carry on from there. Deal. I want to see all 42 of you back. You promise? Cool. Guys, thank you so much. You were awesome. I miss you so much. I will see you on Monday. Be good and be safe. Bye.